There are lots of applications where we not only need to know that an object or a person is nearby, but also how far they are. Imagine a robot moving around in a room. The robot can use a distance or proximity sensor to detect that it's approaching a wall or another object. Or you could use a proximity sensor to automatically open up a door if a person is within a meter of the sensor. You find such sensors in cars to help with parking and to avoid small accidents, and in smartphones, where the smartphone can detect, for example, that the phone is held against the user's head, useful so that the screen is turned off to avoid accidental touchscreen input. There are many types of technologies that can be used to make a proximity sensor. In this lecture, we will focus on the ultrasonic sensor, which is essentially a land sonar. It emits a high-frequency sound far beyond what the human ear can hear and waits for the echo. Once it captures the echo, it counts the time that elapsed between the emission of the ultrasound signal and the capture of its echo, and based on that, it calculates the approximate distance of the object that produced the echo. Later on in this lecture, we'll look at how this calculation works. Ultrasonic sensors are solid-state devices, very reliable and cheap, especially in indoors environments and for small spaces or for measuring small distances. These sensors represent a good choice. Anything that is solid enough to allow sounds to bounce can work with these sensors. If you want to measure or detect things like smoke and clouds, you will need to use something else, perhaps a microwave Doppler radar. For the Arduino, a commonly used proximity sensor is the HCSR04. You can find them on eBay for less than $2 each. The circuit we're going to put together contains the Arduino, 6 jumper wires, and the ultrasonic sensor. This sensor will take distance measurements of whatever happens to be in front of it, your hand, books, etc. The Arduino will receive these readings, calculate the distance they represent, and print the distance to the monitor. It's very simple. Let's look at the assembly now. Let's start with the sensor. Looking at the sensor PCB, we can see that there's 4 pins. There's VCC, trigger, echo, and ground. Trigger is a pin that we use to emit the ultrasound. Then echo, the pin we use to read the echo coming back to the sensor. So let's plug the sensor anywhere on the breadboard. I'm going to set up the breadboard by connecting the ground column and the VCC 5-volt column onto the Arduino. And then I'll connect the ground pin of the sensor to the ground column on the breadboard and the VCC pin of the sensor to the 5-volt column of the breadboard. Then I'll use the orange wire to connect the trigger pin. And a yellow wire for the echo pin. Let's plug it into the computer and upload the sketch to the Arduino. You can see as I'm moving my hand back and forth in front of the sensor that the readings that I'm getting vary accordingly. And that's the assembly. Done with the assembly. Let's work on the sketch now. There's quite a lot happening in this small amount of code. We define the sensor's trigger and echo pins to be 13 and 12 respectively. In the setup function, we initialize the monitor and set pin 13 to be the output and pin 12 to be the input. Through pin 13, the Arduino will ask the sensor to trigger a ping, similar to the boing noise that submarines emit when they use their sonar. This ping, assuming it bounces off an object in range, will come back and will be picked up by the sensor's receiver. The Arduino will know when that happens because it is monitoring pin 12, which is connected to the sensor's echo pin. In the loop function, we first set up two variables of type long. Long numbers are 4 bytes in size, a total of 32 bits, and can hold very large numbers. The variable duration will hold the total number of microseconds that it took for the ping to reach the object and return to the sensor. The variable distance will contain the distance to that object in centimeters. The Arduino is triggering a ping by writing to the trigger ping 3 pulses. First, a digital low for 2 microseconds, then a digital high for 10 microseconds, and finally a digital low, which stays low until the next iteration of the loop. It then uses the function pulseIn to get the number of microseconds it takes for the ping to come back. PulseIn accepts two parameters, a pin number, in our case it's 12, stored in variable echo pin, and the pulse level we want to detect, in our case it's high, because we want to detect the 10 microsecond ping we just emitted. As soon as the Arduino calls a pulseIn function, it starts timing. It returns a number of microseconds from the time the function was called until it detects the ping echo. The distance then is calculated by the Arduino. It divides by 2 the duration that the pulseIn function returned, since the ping travels a total of twice the distance of the object, going there and also each echo coming back. It then divides again by the magic number 29.1. If the distance is over 200 centimeters, the Arduino reports that the target is out of range, since at that distance measurements are not reliable. The same happens if the distance is negative. Any other distance condition is valid, so the monitor will print out the distance in centimeters. Now let's have a look at the distance calculation. It all starts with the speed of sound. The speed of sound at 0 degrees Celsius is measured to be 331.5 meters per second. At different temperatures, the speed of sound is calculated by adjusting 331.5 meters per second for the temperature by multiplying by 0.6. So the formula is speed of sound for a given temperature equals to 331.5 plus 0.6 times the given temperature. If we do this for 20 degrees Celsius, this works out to be 343.5 meters per second. We then need to convert the seconds to microseconds and the length from meters to centimeters. So we adjust the formula to be speed of sound equals 343.5 times 100 divided by a million, and that gives us 0.03435 centimeters per microsecond. This means that sound at 20 degrees can travel a distance of 0.03435 centimeters in 1 microsecond. If a signal and its echo takes x microseconds to do the round trip, then the total distance covered is, and the formula is total distance equals x times 0.03435, which is equals to x divided by 29.1, which is the magic number. We adjust this so that we only include the duration of the one-way trip to the target instead of the return trip, and the formula becomes distance equals x divided by 2 times 0.03435, or x divided by 2, the whole thing then divided by 29.1. And that is how the Arduino and the ultrasonic sensor can work together. Before going to the next lecture, please try out the questions for lecture 11.